Good morning, everyone. My name is Kefei from Tsinghua University in Beijing. First, thank you very much for inviting me for this keynote lecture. I will talk about durability design, control, and planning for concrete structure from our practice in China. Here is the outline of my presentation. I will begin with some fundamental concepts in durability design, and then I will continue on China code for durability, and then I will focus on the review of a recent technical guide of durability of concrete structure called CCES01, and then as application I will give a brief review of the durability planning for Hong Kong, Zhuhai, Macau Sea-Link Bridge project. In the end, I will summarize my talk. Let's begin with the concepts. I think this figure can best illustrate the idea of durability design. Imagine we have when we have some kind of durability problems, our structural performance decrease this way. Here we have a minimum acceptable level for this performance called durability limit states. The intersection here we can measure duration for this intersection point, that is service life, with respect to this performance. So on this figure, the three fundamental concepts for durability design are all present. That is deterioration law, durability limit states, and service life. If we make the design, we begin with the prescription of design, working life, service life. The prescription of design working life is not a pure technical issue. It is also determined by other aspects like economic consideration, legal, ecological constraint, etc. On this table, I just gathered the numbers for design working lives for different civil structures from different active codes all over the world. You can see that on average, we need 50 years also for civil buildings, and for tunnels and this kind of infrastructures, we prescribed more than 100 years. Durability limits is the acceptable level with respect to the deteriorating performance. On this table, I list the possible durability limit states for main durability processes. I take chloride-induced steel corrosion as example. You will see that normally we have an early state like specified chloride ingress extent and a late one specified corrosion extent. Normally, the early states is related to or apply for principal element, high stress wires, or elements with high maintenance cost. And the late state is usually prescribed for replaceable elements or elements with low maintenance costs. And if we want to quantify the deterioration law for performance, we need models. Here, a good model needs firstly to be correct, secondly to be quantified for its uncertainty, right? And then if we use these two criteria, we'll see that although we have a lot of model proposed in literature, reliable model is not that many. So for now, we can just say that for chloride ingress and carbonation depths, we have good models, not for other processes. And the approach, how to perform the durability design, the first approach is prescription or deemed to satisfy approach. In this approach, we start with design service life. We start with environmental action classification. We do not calculate the deterioration, we just use the classification. And then we use this deemed to satisfy approach. normally represented by a series of tables. And then from these tables, we derive directly the requirements on material quality, protection measures, and element details. And if we have models, we can perform model-based or performance-based design. That is, we know the design service life. We can quantify the environmental actions, and then we use the model with respect to clearly defined DRS. And then from the result, we derive the material quality, protection measure, and element details. And today, there is a transition ongoing. That is, for a long time, we regard concrete as the only valid barrier or resistant to environmental actions. But recently, we have a lot more new materials, protection materials, or technical measures to protect, for example, the embedded steel against the corrosion together with the concrete cover. For example, here we can apply the coating or sealers on the concrete surface. We can use inhibitors to reinforce the concrete cover against corrosion, and we can strengthen the concrete steel interface, or we can use directly weathering and stainless bar to protect the steel bar. So this is a transition ongoing, and we all know that to maintain the durability performance of a structure during a long service life, we need to perform maintenance works. It's very similar to DRS. We need to specify the deterioration level of maintenance, DRM. If we have a low DRM, that means we have lower quality requirement, and fewer intervention. If we have a higher DRM, that means we have a high quality requirement and a lot more intervention times. And moreover, we should note that if we take a low DRM, that means at the same time it's easy to detect the limit states. If we take a high DRM, that means we normally need instruments or sensors to tell us when to start the intervention. And then I will talk about a little bit the evolution of Chinese code. All the stories started in 1999. In 1999, China Academy of Engineering carried out a very serious and comprehensive investigation on the service states of all civil structures. Here are the results. I do not read out the numbers. You can see that. And the situation is far from satisfactory. And the situation is also very urgent, knowing that at that time we have a very, very large scale of infrastructure to construct. So there's urgent need to increase the service life, at least for new structures. That is the reason of being of our first national guide to durability design and construction of concrete structures, CCES01. And the objective is very clear. It's very urgent. It was very urgent also. It's to provide a method for durability design and technical measures in construction to increase the service life of concrete structures. So here I list the main content of this guide. You can see that it included environmental classification, service life, design procedure, requirements on the concrete materials, detail and crack control, and construction requirements, and additional protection measures. In the appendix, we have the text method for durability. And here, I would like to pay tribute to one of our pioneers, in durability research study and code drafting. It's Professor Chen Zhaoyuan who passed last year. It's him who led all the drafting of this series of code and standards. And soon after this code, this guide, we formalize the requirement into a design code. That is the design code for durability of concrete structures. It's finished in 2008. And you see that we formalize the requirement into design basis. Here we have the environmental classification, service life, etc., and the durability requirements for all different kinds of environments, and also some requirements for post-tension concrete structures. So in the appendix, we have raw materials requirement and a test method. And I believe this code promotes very much the durability design works in China, and I think it contributes actually to the increase of service life of newly built structures. After 11 years of use of this national code, we 2 years ago we update the content of this code by the requirement for pre-stressed wire, construction method, maintenance design, use of C-sand, using corrosion-resistant steel, multi-layer protection, and model-based design approach. And after this drafting, we think we turn back to the mother document of all this code, that is CCES01. Today, we think that it's better to alternative to the design code, we leave a document to provide technical solution to durability durability of concrete structures. And we just finished the draft work, and in this draft we update the specification provision for durability on the basis of state art of knowledge. We push forward the performance-based design, and we provide systematic solution to assure the durability design working life through durability planning. Let's concentrate on the technical guide CCES01. Here is the document structure. The document is composed of 9 chapters and 4 appendix. Chapter 1 is the general, including aim, scope, usage of this document, followed by terms and symbols. And then it's the basis for this document, including environmental classification, design working life, design considerations, and maintenance design. Structural materials include concrete and steel. Detailing and concrete crack control include general roles, concrete cover, and crack control. And then we have a requirement for construction for additional durability measures, including coatings, corrosion inhibitor, cathode protection. And Chapter 8 is dedicated to post-tension pre-stressed concrete. And Chapter 9 is the maintenance design works. And appendix, in the appendix we have test method for cracking resistance, test method for durability indicator, durability model, and the test method for bleeding of grounds. In the basis, we set up a general framework to assure the durability here by the Article 311. That means to assure the durability of concrete structure, we should adopt technical requirement and consideration in design, construction, and service phase. In design phase, in durability design, we should determine the material properties, structure details, and additional protection measure, etc. And during the construction, we should assure make the quality control, especially for durability, including the control over raw materials, assure the compactness of concrete, positioning of steel reinforcement, and to prevent cracking. And during the service life, we should install rational maintenance scheme. That is the framework to assure the durability in life cycle sense. And then this CCES01 divided the environmental actions into into 5 environments based on the deterioration mechanism. The atmospheric environments refer to the steel corrosion induced by carbonation. Free thaw refers to the concrete damage from frost action. Marine and de-icing source or both refer to the steel corrosion from chloride ingress, but from different sources of sorts. And chemical environment refer to the concrete damage by several damage, including the chemical in groundwater and soil, salt crystallization, and air pollutants. And each environments, we specify further the intensity of the action. The intensity, we have 6 classes of intensity, from A, very slight, to F, extremely severe. And from this table, you can see that each environments we will cover 3 or 4 different intensity. And I will make an example to show how we quantify or assign the different grade of intensity to environment, marine environment, the environment 3, for example. We all know that in this environment, the risk comes from the chloride ingress to surface of steel bar, and then the steel will be depassivated, and we will have the electrochemical reaction of corrosion. That means we have the anode reaction and cathode reaction. To make it happen, we need some conditions. First is the chloride, sufficient concentration of chloride on the steel surface, and oxygen and water to make the cathode reaction possible. So if we apply this mechanism to a marine exposed structure, we can see that in the splash zone of exposure, at the surface we have a drying wetting action, leaving very high chloride concentration on the surface, and we have in this zone we have also the alternative availability of oxygen and water, which are very favorable to the corrosion. So on the basis of this analysis, we look at the environmental factors, including the chloride exposure condition, humidity condition, including drying and wetting, and temperature. And for example, for immersion, permanently immersed in seawater or water-saturated soils, we are treated the lowest grade. It's the C3C. It applies to a pier or bearing platform or foundation immersed in water, because in this exposure there is very little oxygen to support the continuous corrosion. On the contrary, if we have exposure to tidal splash and run, we have much higher intensity. In the tropical climate plus the splash and run zone, we attribute the highest intensity 3F. And design working life, here on the table, we just gather the requirements on the design working life for different buildings and constructions. We divided into 3 categories: 100 years, 50 years, and 30 years. For design working life, there's one remaining question. That is how to assign design working life of whole project to elements. Here we think for civil buildings it's the same, and for bridge and tunnels if we have replaceable elements, the elements can have shorter working lives. And for elements without access for maintenance, that is very difficult to maintain, these elements should have the same design working life with the whole project. That's the principle. On this table, we summarized the durability design works should be done, which should be done during the design phase. You can see that the tasks are distributed in terms of the service life and the intensity of environmental action. For the most severe action, you can see that we need to finish almost all the works related to the durability of concrete structures. And the last thing we consider in the design phase is the maintenance design. We say that maintenance is very necessary. Maintenance design should take the starting point as the end of construction. And what maintenance design will do is to determine the rational techniques and intervention frequency or scheme for maintenance, considering the service condition and the performance deterioration of structural elements. Here, we just show two cases of different intervention scheme. One is called a real-time scheme. That means if you have three groups of elements here which deteriorate with different rates, real-time means whenever a group reach this DRM, we start the maintenance. And the synchronized scheme here is another organization. That means we look at the most fast group 1. Once group 1 reach DRM, we will start the maintenance for all the groups. Of course, for this scheme, we use out all the potential of durability performance of all groups, and for this cases we waste a little bit the potential, but the advantage is the intervention times in this scheme is fewer. Perhaps somewhere is also an advantage. And then we continue on the chapter 4 for the structural materials. For concrete, the requirements for concrete are formulated on the basis of environmental classification and design working lives, and the requirements are formulated for both concrete composition and properties. The most important property here is the minimum strength for concrete here. And in parallel, we introduced the concept of durability indicator like chloride diffusivity, water permeability, and gas permeability. Because we think that whatever the phenomena of durability is, it more or less or relate to the gas transport, ion transport, and water transport. So we think that whatever you use as durability model after design, more or less you can transfer your requirement parameter into these three parameters. Following this line, for example, we formulate the requirement for the structural concrete in atmospheric environments. Here, you can see that on the table, we use the parameter of porosity, gas permeability, and water sorption rate, plus the minimum strength. That is the property requirements. Of course, in parallel, you will see that we have also requirements on the composition, like maximum content of fly ash and slags. So it's a mixed approach between the deemed to satisfy prescription and the performance-based requirements. And for reinforcement steel here, you can see that we recommend the use of epoxy-coated bar, galvanized bar, weathering-resistant bar, and stainless bar. Here, I just show you how we gave the provide the requirement for stainless bar. You can see that we formulate the requirements in terms of the exposure, environmental action, intensity, and the service life, and also in terms of the PREN value of this stainless bar. And we continue on the details. On the details, most important, I think, the detail to protect the steel corrosion is the thickness of concrete cover. Here, we gave the requirement on concrete cover thickness for environment 1 and environment 3 and 4. They are all related to the protection of steel corrosion. Here, I can tell you that the value here are very consistent with the Eurocode requirement. And another control is the crack control with respect to durability. Here on the table, we limit the surface width opening with respect to exposure classes. It's also very similar to the requirements of Eurocode, but here, I would like to say that from the recent laboratory study and a long-term exposure test, they confirm that the crack surface opening width is not very relevant to the corrosion in crack. They confirm also the relevance of concrete cover compactness also. So we think that with the further study, perhaps this requirement on the surface opening width will not be so important. And then we'll continue on the requirement of construction. On construction, first is on the raw materials. Here I give you the article concerning the Portland cement. You can see that we put some requirement on the characteristics and composition of the cement, and some environmental dependent requirement on C3A, for example, with respect to the environmental type and exposure classes. And then we give some instruction or requirements on the proportioning. For example, for a different grade of concrete, we impose the maximum water to binder ratio, the minimum and the maximum content of the binders. We impose also the limitation of chloride content with respect to the different environmental action, means type and intensities. And for concreting, the article are very detailed. Here, I just show you is covered from the construction organization until the demolding, curing, demolding. Here, I just show you how we required the temperature of the mixture, concrete mixture, before entering the mold, because it's one of the important factors to determine the early risk of cracking in concrete construction. Here you can see that some temperature is given. And then we put the requirement on the construction inspection. The reason for this is, whether we use durability indicator or not, they are all parameters based on laboratory test. The real quality indicator, the most pertinent indicator, are to be measured directly on the surface of the finished members. That's the idea. So in that sense, we need to make the inspection of the durability quality of the hardened concrete members. So in this article, we just set up some basic rules to make this kind of inspection. For example, to measure the concrete cover thickness, compactness, air content, average void spacing, and some transport property. And then in chapter 7, we prescribe the protection measures. That means the measures, technical measure and materials to support the multi-layer protection in this guide. Here we, in terms of the different environmental type, we proposed a different combination of possible protection combination in different exposure. For example, here on this table, we gave the detailed possible solution for very serious E and F grade intensity for protection lives less than 20 years or more than 20 years. These are the solutions. And in the last part, we prescribed the durability requirement on the post-tension pre-stressed. Post-tension pre-stressed is special because the corrosion of this steel or strength will endanger directly the safety of the structure. So in this chapter, we apply mainly the multi-layer protection for tendon and anchorage. Here we can see that, for example, for tendons, we from inside to outside, we have respectively the protection measures as the coating for tendon, duct filling, duct or pipe, the concrete cover, and the sealing coating on external concrete surface. And on this table, we just attribute this combination, the combination of to the different environmental classes and intensities. Generally, for the most severe exposure, you need all. For some very slight action, you need only 1 or 2 measures to counter. Okay. So the last chapter of this guide is on the maintenance. It's written in the sense of life cycle management. So in this article, you can see that the life cycle management of this concrete structure should be include the regular inspection, durability monitoring, and elaborate the maintenance planning based on the preliminary maintenance design planning in the design phase, and evaluate the durability performance and update the maintenance scheme and in inspection interval using the assessment results, which is a dynamic process. So we apply these ideas in the foregoing code to the durability planning of a large-scale sealing project. This sealing project is the Hong Kong-Zhuhai-Macau Bridge, which link Macau, Zhuhai, and Hong Kong by a huge mega project, which includes more than 20 kilometers sea bridge, 2 artificial islands, and a segment of immersed tube tunnel of 6.8 kilometers. And the design working life of the whole project is 120 years, and it was open to traffic in 2008. Our team were involved in the durability design of these concrete structures. The first strategy is to divide all the durability process into 2 groups. For the low risk groups here, we control the durability risk through the qualitative raw materials control. And for these 2 high risk groups, we can only control the durability risk through quantitative model-based design. Here is the durability requirement prescribed or to be prescribed both on material level and the structural level with respect to the different process. And if we want to use model-based approach, we need to know the design life, service life, the DRS, and here are the choice of design service life and the DRS for the main concrete element in question. And for a chloride ingress, we use model-based design. The model is from is like the model in Deterioration. It's a diffusion second fixed law diffusion from diffusion process, and with an aging diffusivity, and that is the design function. But to apply this equation model to Hong Kong-Zhuhai-Macau-Xilen Bridge, we have two problems to overcome. The first is we have to take into account the statistical property of all these parameters. In this way, only in this way, we can have some design margin. And the second thing is these parameters are all environmental dependent. So we have to calibrate this model on the local data. So fortunately, we have long-term exposure data on similar sites available to us, and use this data. We calibrate the partial format. We design equations from the full probabilistic formats, and here are the results. That means the target reliability index is 1.3 for 120 years, and on this figure is the result is that we prescribe the chloride diffusivity in terms of the service life and concrete cover. Using this, engineer can continue their design work. And when we go to the construction phase, the problem is our value from the model is the diffusion. It's a diffusion coefficient. But in the laboratory, at the quality control level, we have the migration values. These two values are not equal one to the other. So we have to make the conversion. That means we reconstitute the long-term exposure specimen in laboratory, and we do again, we redid the migration test on this specimen, and we regress the correlation between the two. In this way, we can convert the design value to quality control value. And during the construction, we collect all kind of data for concrete cover, for chloride diffusivity. We use the same model to update or to make the durability assessment during the construction. Here is the result. You can see that it's always within the consideration or within the design margin. The only thing is here we have an accidental consideration case. It's not a normal working case. It's a little bit higher. This is accidental case. So after this, we set up a maintenance planning framework for the life cycle of this project. That means after construction, we have a assessment. That is this assessment. And during the service life, on one side we have the inspection and monitoring, and on the other side we have a maintenance during service, and we can provide record and data to assessment. So regularly we will set up activate this durability assessment to see the up-to-date durability level, and then we decide whether we need to redesign the durability or update the monitoring or the maintenance works. So that's all the content of my lecture. So let me conclude my lecture by these words. First, I think that the durability design of concrete structure, the fundamental concepts are widely accepted, and today we tend to incorporate more and more life cycle elements into durability design. That's the trend, I think. The second thing is rational maintenance design and planning is very crucial. So I think more elements should be incorporated into this design. And now more and more reliable protection material and technique are available. And I think the transition from one layer concrete cover strategy to multi-level strategy is ongoing. And the last point, by the application to Hong Kong-Zhuhai-Macau Sea Bridge, we can see that we demonstrate how this 120 years of service life is assured first during the systematic durability design, and then through the quality control in construction, and finally by dynamic maintenance planning during the service phase. So that's all for my lecture. Thank you for listening.